Hello guys, welcome to the beach tutorial. Welcome to the beach tutorial. Now, in our previous class, we talked about electrostatic, where I talked about the application of the Coulomb's law. We talked about applications of Coulomb's law, and we also talk about capacitor. We also talk about the capacitor. So if you are here to get those videos, you can just go online to YouTube, text the beach tutorial. You get the videos there. Now today we'll be going into something different. We are going into electric field intensity. Electric field intensity of multiple charges. So this is the topic. Now I would like to take it one step at a time. We are going to talk about electric field intensity itself before I move to multiple charges. Basically, in the previous video we deal with just 2-point charges, the positive and the negative, and they are separated by distance r. That is, you have q1 separated q2, and you have a distance r here. Yes, which is their separation. But then in this particular class, we'll be talking about multiple charges. When you have multiple charges, to calculate the electric field intensity, we make use of our vector diagram and vector sum. Now let's take a look at this example. Okay, before we move on, electric field intensity is given as, we have the first formula we are familiar with is F over Q, where your F is the force. On test charge. On test is the force on the test charge, and the Q is the magnitude of charge. So the second formula is E equals KQ over R squared. So we'll be working with either of this formula, but mostly we'll be dealing with this formula. Now you know that we were made to realize that K is a constant, and the value is 9 times 10 raised to power 9. I explained this in the previous class. Newton per meter, Newton meter square, Coulomb square. Yes, I gave this out in the previous class. So if you are ready to get the video, please go on to your YouTube channel, go to YouTube and check our channel there, the beach tutorial. You get the videos on physics and chemistry and also mathematics there. They are all available. And now so basically let's look at some questions. Let's solve some questions. Now we are given a question here, example 1. The question is 3-point charges. 3-point charges of magnitude 3-point charges of magnitude plus 3 microcoulomb minus 2 microcoulomb, and the last charge there is minus 5 microcoulomb, are arranged. So we'll be given their arrangement, are arranged as shown in the figure below. So you guys should copy this down before I move to the next page. 3-point charges of magnitude plus 3 microcoulomb minus 2 microcoulomb and minus 5 microcoulomb are arranged as shown in the figure below. So basically let's go straight to the figure below, and we're going to solve it together. Now what we have here is this. So let's divide the page. So this is point P. and this is our plus 3 microcoulomb. You have it here, and here you have a minus 2 microcoulomb, and at the top we have a minus 5 microcoulomb. So we're made to realize that this height, so we're made to realize that this height from here to here is 7 centimeter, and from here to here is 6 centimeter, and from here to here is 4 centimeter. So basically this is the diagram. This is the arrangement. 4 centimeter for our 3 microcoulomb, 6 centimeter for our minus 2 microcoulomb, and 7 centimeter for our negative 5 microcoulomb. So the first thing to do is this: we calculate the individual electric field intensity. That is, we calculate electric field intensity of plus 3 microcoulomb. We also calculate electric field intensity of minus 2 microcoulomb, and we also calculate electric field intensity of minus 5 microcoulomb. So basically these are the individual electric field intensity. After calculating all this, then we draw out the vector diagram and we calculate the net electric field intensity. That's the overall. That's when we make use of our vector diagram. Now let's start with that of 3 the plus 3 microcoulomb. So let's calculate the intensity. And don't forget, if you are to get the intensity of that, the formula given to us is that electric field intensity E is given as electric field intensity E is equal to KQ over R squared. So, and that's equal to, our K is 9 times 10 raised to power 9, then times 3. This is the charge here. So micro is times 10 raised to power, don't forget, minus 6, then over, this is 9, minus 6, and over, don't forget our separation. Now the separation here is 4 centimeter for 3 microcoulomb. So we need to convert it to meter, and that would be 0.04 meter. So 0.04. And the formula is R squared. So we need to square it this. So for our plus 3 microcoulomb, let me clear the whole page. I believe you guys have this illustration with you. So let's clear it. So the next page now, our intensity will now be equal to, if you do the calculation, we get 16.9 16.9 so that will give us 16.9 times 10 raised to power 6 Newton per coulomb. This is the answer for intensity at plus 3 microcoulomb. Now don't forget, we calculate that of minus 2, and that will be E of minus 2 microcoulomb. So E equals KQ over R squared. So our E will be equal to, our K is 9 times 10 raised to power 9, 9 times 10 raised to power 9, then times our Q. What the charge we are considering here is for -2. So don't forget, this negative sign is only telling us that the unlike charges we attract. So we just put the times 2 times 10 raised to power. Now if you have micro here, so micro is a minus 6, that's what you have there, then divided by our separation. The distance given to us there is 6 centimeter, so that will be 0.06 all squared. So the electric field intensity for -2 microcoulomb will be equal to 5.0 times 10 raised to the power 6 times 10 raised to the power 6 Newton per coulomb. Newton per coulomb. That's the answer. So the next thing we now do is to get the electric field intensity of the last point charge. That is -5 microcoulomb. So of -5 microcoulomb. So what we have there is E equals KQ, the same formula, over R squared, and E will be 9 times 10 raised to the power 9, then times our charge here is 5, so that's 5 times 10 raised to the power -6, our micro. So -6 divided by R squared. Now the distance given to us there is 7 centimeters, so you convert to meter, and when you convert to meter you have 0.07 meter all squared, and the last intensity here is for -5 you have 9.2 times 10 raised to the power 6 Newton per coulomb, times 10 raised to the power 6 Newton per coulomb. So these are the individual electric field intensity. They are the individual electric field intensity. Then the next thing we need to get is our overall. Now there are some conditions you follow to get your now let me just put it there. To find net, we are still solving the same question. To find net electric field intensity, to find the net electric field intensity. So basically this is what we want to calculate, the overall. The first thing you notice that when you have negative sign, that is when you are sketching the vector diagram. You understand now? When you are sketching the vector diagram, the field line of a positive charge are radially outward. They point away from the charge. Let's say for instance you have this. Let me just show you guys this before we continue with the question. This is what we are solving. You have negative, here you have positive plus 3, and here we have negative. Now if you want to draw the vector diagram for this, now this is what they're trying to say. Here the sign here is positive. That implies that the charge will be moving away. The arrow of field line will be moving away from this charge. So you have it going inside, that is towards this direction. But when you have a negative sign like this, what will happen is that the field line will be moving towards the charge. And here you also have a negative. The field line will be moving towards the charge. This is the charge. This is the charge here. This is the charge here. And this is the charge here. You understand now? So, but the difference between what you have there is that for this positive, the field line was moving away from the charge. But for the negative here, the field line was moving towards it. For the negative here, the field line was moving towards this, but away from this. Now, that's how to calculate our net field intensity. So, what I'm going to do is this. Let's solve the question given to us. So, we are going to apply this method. Don't forget the condition. Now, if you have to solve this, so let's start. So, I will draw the representation again. We are given this to work with. So, here we have -5 microcoulomb. Here we have plus 3 microcoulomb, and lastly here we have -2 microcoulomb. This is where you have our P. It's still the same representation. Now because this is one point charge, this is another point charge, and this is another point charge here. Now this is positive, so the arrow will be moving away from this charge. You understand now? And this is negative here, so the field line will be moving towards the charge here. and this one is negative, so the field line will also be moving towards it. So this is the vector diagram. This is the vector diagram, and that implies that if you look at our -5, the direction is positive along y, is positive along y, because this is the direction of our y-axis. And if you look at for this -2, it is positive along x. If you look at +3, +3, it is also positive along x. Sorry, don't mind that. It's also positive along x. So we'll be working with that. Now, we'll be working with that. Then the next thing to do is this. Now we know that all the point charges are positive. Then we get it overall. You now tell us that this our line is our what? Horizontal. Don't forget, this is horizontal and this vertical line. So we are going to calculate the vector sum, the summation of E. You understand now? Horizontal, horizontal, horizontal. And on the horizontal line, we have our +3. We have the +3 microcoulomb and the -2 microcoulomb. Don't forget, on the vertical, we have our -5 microcoulomb. So what we need to do now is this. To get the summation of E horizontal, this particular aspect is quite cunning and confusing. You just have to focus now. So summation of E on the x-axis will now be equal to, don't forget, we have this and this. So you write out their E value. That is E of +3 plus E of the -2. You understand now? So from here, when you sum it up, the E of +3, that will be 16.9 times 10 raised to power 6, then plus 5.0 times 10 raised to power 6. So at the end of the day, what you get is 21.9. 21.9 times 10 raised to power 6 Newton per coulomb. Please note this. What we calculated there is summation on the horizontal line. Summation on the horizontal. So we still need to work with this vertical. Now, and you know, on the vertical, you only have one charge there. On the vertical, what we have there is for our -5 microcoulomb. So that's quite easy. Then for us to get the net force now, electric field intensity. So the net. So for us to get the net electric field intensity, EI, that will now be E equals summation of so you have this. So you open the bracket, summation of electric field on the x all squared plus summation plus, sorry, so don't mind the board anyway, that's bound to happen. So, and summation of E on the y. So basically, this is how we are going to get the vector sum. That is the sum of the intensity we have to calculate. And if you look at that, that will lead us to square roots of, for our summation of x, what we calculated the other time was 21.9, then times 10 raised to the power 6 all squared, plus for the y, which is the only one for -5. Don't forget, for our -5 microcoulomb, that's the only one we have on the vertical axis. Don't forget. So basically, we just write the value. That's 9.2 times 10 raised to the power 6 all squared. So by the time we take the square root of everything, our total intensity will now be 23.6 times 10 raised to the power 6 Newton per coulomb. So this is the final answer this is the first example. In the next video, I will upload the second example on multiple charges. Don't forget to subscribe to the YouTube channel so as to be notified when other videos are uploaded. Yeah, thank you.